Okay, so next, we have to define, we need probability distributions. We need to deal with the idea of probability in stat mech. And it's, you don't need a lot of it, but you need to know the basic concepts pretty well. So let me just motivate this. So statistical mechanics, gives rise to macroscopic laws of thermodynamics. And what you can think of is that you can think of, for example, the macroscopic quantity of pressure of a gas as arising from the statistical, from the kinetic energy of the particles, colliding against the wall of the container. You have seen this in thermal physics, I presume, right?
Yes, sir.
But you know that not all the molecules are going to have that same average energy, right? The pressure is the momentum imparted by the gas. The kinetic energy is the temperature. But you know that there's going to be some variation, that not all the particle is going to have the same kinetic energy, or is not going to impart the same momentum. But at the same time, so it's about it's about what is the so you can have different kind of averages coming out. You can have different different predictions, but so we have to calculate what is the most probable thing. What is the most probable pressure, or most probable temperature. And it turns out that's really, because we're dealing with large numbers, that's really what we observe. So so this is a very so this is a very brief sort of very hand waving. This is a very hand waving motivation for probability, but you know what I mean. So so let's look at probability distribution, and let's start with, say, discrete probability distributions. Okay, we start with discrete probability distribution. Sorry, my cat wants to join the class too. Hey, Chaka. So the discrete, so let X be a random variable. A random variable, and for now, let it be a discrete random variable. Do you know what a discrete random variable is?
It can only be an integer.
Right. No, it doesn't have to be an integer. That's not, no. It doesn't have to be an integer. It just has to take values from a discrete set.
Okay.
So what is a random variable? A random variable is a variable that takes its value from a set according to some probability distribution, and a discrete random variable is a variable that takes its value, say X takes its value from some set, say let's call it, say, xi, where I goes from 1 to n, and with, say, a probability distribution with probabilities say P of x1, P of x2, dot, 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 P of xn, okay? So the fact that, this is a discrete set is what makes it a discrete random variable. The values that the random variable takes doesn't have to be integer. Even it doesn't even have to have a particular, a lot of times it's arbitrary almost. Like you can have head or tails. You can, for example, for a coin tossing experiment, you can think of the value that the coin toss takes as a random variable, and it can be 0 or 1 or plus half or minus half. There's lots of flexibility there. Okay. So once you have a random variable, an important characterization of the probability distribution. So this is a probability distribution. So the probability distribution is characterized, an important number is the average or the mean. So you can also think of it as the 0th moment. Okay. So what is the, I mean, I will come back to this whole moment thing a bit later on. So what is the average or the mean? So the average or the mean is of a function of the random variable. So we don't always have to take the average of the random variable itself. It can be any function of the random variable, right? So suppose f of x is a function of the random variable x, then it's average. And sometimes it's written like that. Other people write it like that. As a physicist, I like this notation. And this is given by the summation over the set of the value of the function evaluated at the particular value of the random variable times the probability. Okay? Now, we are assuming that our probability distribution is normalized, meaning that the sum of all the probabilities is 1. Now, this may not be the case. Probabilities can be relative. If it's relative, then we have to divide this by sum of all the probabilities. Okay. Otherwise, this will not be the correct value of the expectation value. So, of course, when it's normalized, so from now on, we are going to assume it's normalized. So this is going to be 1. Okay.